So you've all used them. You use files every day, and that's something that's sort of been conspicuously absent from our own programming activities in this class, accessing information from a file, right? Give me an example of where you in your everyday life use files. Yeah, like you save a Word document, right? Where do you save that information? You name a file and it goes on your desktop. And say you want to send that essay to someone via email. What do? So you type the email and then you attach. And typically when you do attach, what happens? You have to go find it, right? Go find the file, click on it, attach it to the email. The file has the information representing your essay. That's what we want to talk about. Not for very long. I'm not going to really dwell on this particular topic for too long, but for, say, today and Wednesday, perhaps, we'll talk about reading and writing files. Let me show you the homework assignment that is due. When is it due? It's due next Monday. So let's talk a little bit about this homework assignment. Most people are familiar with the number pi. It comes up in geometry. It has a lot to do with circles and so forth. And probably most people know that pi is irrational, but they might not really know what irrational means. And other people might not know that it's irrational, but they might know that it's an infinite non-repeating decimal, pi 3.14159, yada, 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 and it just goes on as long as you'd like. There are massive industries out there, and I'm sort of exaggerating, but a popular pastime among computer scientists and mathematicians is to actually compute digits of pi. We may be up to like trillions now. I don't know. I guess we could check and see. So I don't know. If you type in digits of pi, there's 5 trillion digits of pi. Yeah, you would, right? The reason people do it, there are a couple of reasons. One is for very large numbers of digits, it's actually just an interesting computational problem, right? How do you get those digits? How do you generate those digits? And for mathematicians, there's a guy, I think he's at University of British Columbia right now, John Borwein. Anyway, it might be his brother Peter, I don't remember. But one of the two, it used to be that, 3.14159, if you want to generate the next digit, you kind of had to generate all the digits leading up to it, and then you would generate the next digit. And these two guys, Peter or John, I can't remember which, actually went back through mathematical methods, actually came up with a way of just diving in right in the middle and saying, I want the millionth digit of pi, and you can use their method and jump in and grab the millionth digit of pi without having to compute the first 999,999. So it's an interesting abstract mathematical problem that people struggled with for a while, although I would say with the advent of this technique, it's a little bit less interesting than it was. And then it's an interesting computational problem. The other thing is, are there patterns lurking in pi? The more digits you can generate and the more analysis you can do on those digits, it raises the possibility that, in fact, it's not. We know that it's an infinite, non-repeating sequence of digits. Do we know that it's random? Do we know that it's random? That's an interesting question. Or are there some statistical things that we can say about, for example, does 9 occur more often? Or does 3 occur more often? Right? At this point in time, it appears that the digits are uniformly distributed. The likelihood of getting a 1 is the same as the likelihood of getting an 8 or what have you. So there are interesting statistical questions about the digits of pi. So what we're going to do, I'm going to provide you with a file called digits.txt, and this file has 1,000,000 digits of pi in it. And that's literally all it has. I've stripped out everything else, the decimal point, and also this. You know how we talk about end lines in here a lot? There are no end lines in here either. It's all just one long line of text, 1,000,000 characters long. And what we're going to be doing is opening a file that contains these 1,000,000 digits, asking the user for a string of numbers, like our zip code, 99362. And then just starting at the beginning, and is that 99362? No. Is that? No. Is that? No. And just going all the way down until you find 99362. Let me show you a demo here. So here's my version of it. This program will search for the first occurrence of a string of numbers. If I type in the zip code, it says that it's about 7,000 digits in. You'll find 99362. Let me do one that's a little more believable, just so that you actually feel reassured that this thing is doing the right thing. Let's punch in, for example, you see this guy right here, 592? Right, that's 1, 2, 3, 4, 5. So if I punch in 592, since that's the first time 592 occurs, my program should report a 5. We could do 653, right? And it's at location 8. That's essentially it. That's what you're going to be doing. And then the other aspect of this thing is to just play around with it a little bit. So I've got some specifications about how this should work. And then down here, I'm asking you to use your program to find interesting numbers, home zip code, phone number, yada, yada, yada. And then there's this table down here, which is also a little curious. Why we would care about, say, 6 sevens in a row versus some other number, we don't really care. It's just kind of a curiosity. But I asked you to fill in this table. So, for example, what's the first occurrence of 1 0? What's the first occurrence of 2 consecutive zeros? What's the first occurrence of 3 consecutive zeros? 4 consecutive zeros, 5 consecutive zeros, and 6 consecutive zeros. And then do that all the way down for the rest of the table. What's interesting about the digits of pi, assuming they are truly random, is that any finite sequence of digits can be found in the digits of pi. Somewhere in the digits of pi, there are 150,000 zeros in a row. Somewhere in there. Guaranteed. It's fascinating to think that any sequence. Yeah.
So this might be a dumb question, but when they say pi never repeats itself, obviously they're like strings of 7 digits that repeat themselves. What do they mean?
Well, I think what they're trying to do when they say that is, they're implying some sort of randomness. Okay, so we do know that they're random in a sense. What we don't know is that maybe they're random, but they're following some sort of non-uniform distribution, which might be interesting. Although it might even be known now. I am in no way an expert on the digits of pi. It's possible that it's known that the digits are uniformly distributed. But that said, sorry, remind me your question, Kendall.
Well, just how can they say it doesn't repeat it?
Okay, so the rational numbers, like 2/3, right? 2/3 is 0.6666666 all the way as far as you can go. That's a repeating decimal expansion. It's infinite, but it repeats. It has a pattern. And any rational number, what do I mean by rational number? I mean an integer divided by an integer. Every rational number ends in a repetitive sequence of numbers. Every rational number's decimal expansion ends in a repeating sequence. Every irrational number's decimal expansion doesn't repeat. There is no repetitive pattern. Does that answer your question, Ish?
Kind of. So they're just saying that like it never starts over and goes back to like 3, 1, 4.
Exactly. Yeah. Or not even that. It doesn't have to be start over at the beginning. It's even that it doesn't get to like 664 and then 100 digits down the road do 664 yada yada yada, right? I mean, it might not start over again here, but it never repeats even in any sort of even at any position. Let me show you some like I need more digits. Okay, 7/11. I'm just sort of winging it here. Let's try 18/11. Okay. So you can see the repetition, but the 1 never happens again. Right? So that can happen, right? You get a few digits at the beginning that are unique, and then you get this sequence that repeats forever and ever. And pi doesn't do that either. And every rational number does that. Trying to find one a little more interesting, but anyway, so that one actually does totally start over again. 18, 18, 18, 18, 18. Okay, enough about that. Let's talk about runs a little bit. So the first occurrence of 0 is at 33, which is actually pretty far down the road when you think about it. Right? The likelihood of 0 occurring is 1 in 10. And yet you've got to go down the road 33 slots to find the first 0. So that's kind of interesting. Let's see if we can see it here. Looks like that's it right there. Yeah. Okay, how about 2 zeros? 308. 3 zeros? 602. And a string of 6 consecutive zeros does not occur in the first million digits. So how would you fill out this table? 33, 308, 602, 13, 391, etc. And then you can go on and do 1. 1 occurs pretty early. 1, 1. And it sort of craps out there. The actual occurrences of these runs is somewhat random, but they do actually follow very well-defined probabilistic curves. So you can see each time I add a 1, I'm sort of adding an order of magnitude to where it first occurs. And that can be made sense of probabilistically. If you're really sharp, you can actually write a little program that will generate this table for you. Okay? So if you don't want to play around typing in consecutive 1s, consecutive 2s, consecutive 3s, just write a program to do it for you and print out the table. All right, any questions about this? All right, the file that holds the digits is right here, and somehow my C++ program is opening up that file and accessing the digits, and that's what I'd like to talk about for the remainder. Before I do that, who's up today? Is it Kuba? Do you want to go ahead and do yours, and then we'll talk about opening external files.
Again.
Yeah, here.
Okay.
It's annoying. Let's go. Let's go here, I guess, and I'll sign out. And then, what is it? Whitmail?
Dot Whitman. Yep.
Okay. See if that
Okay.
does it. That looks like success.
There we go.
Okay. Let me know when you're ready.
Okay, good. So, I'm going to be talking about Alice today. And Alice is an object-oriented programming language that's used to educate school kids, but also beginning programmers. It uses 3D models to basically create animations in a visual world. Originally, it was developed at the University of Virginia in 1997, and then under the guidance of the same guy, it was released by Carnegie Mellon in 1999. And today, there have been 3 versions that have been released, the latest of which was released in 2009. And according to their website, it's used by more than 15% of US colleges and universities. And now Sun Microsystems in California, I think it is working with Carnegie Mellon to globalize Alice. So they're translating into different languages. And then in terms of the interface, they kind of have to match it to each culture. So there's some interesting things with that. So this is like a typical setup for Alice. It basically works by kind of tricking the user into learning to program by making them create movies and video games. So they have this drag and drop interface where the user can like select an object and then it appears as a 3D representation on screen. Right here you can't really tell, but they selected an ice skater and it's right there. And then one of the first few functions, they move up so you can see the ice skater. But there's like a huge variety of objects that you can choose from, and then all of those have their own unique set of functions. And we know that functions affect an object's behavior. So with every object, the user can add different functions to make it do certain things. Like for the ice skater, there's turn, set pose, skate backwards, skate, simple spin, those types of things. And then some of those functions have parameters. So again, it's sort of tricking them into using computer programming lingo without actually teaching them the language. And then the way that they make their animation is by creating methods, which are they're basically like sequences of functions that go together to make complex concerted movements. So when the user runs their program, it'll be going through all of these methods, which have a bunch of different functions inside of them. And these are just screenshots of an animation that might be done with an ice skater. I guess up there she's turning, down here she's spinning around a pole. So there are quite a few advantages of Alice. The first one being that it's very visual, and a lot of students and adults alike are visual learners. So being able to see what you do with your objects when you create them is really beneficial and also effective for getting people interested in computer programming. A lot of students are motivated by storytelling, especially when they can tell their own story. So in Alice, they sort of create their own animation or video game. With the drag and drop interface from this picture, it's basically impossible to make any syntax errors. So that kind of encourages people, because if they kept making errors, they might not like computer programming. Students get to understand control structures and the basic logic of programming. And even though it's sort of written in a Java-like structure, it's very applicable to other computer programming languages like C++. It's pretty similar. The main goal of Alice is basically to encourage students to learn more interesting and complex programming constructs so they can create more interesting worlds. Again, with the tricking them, if they want to create different sorts of animations, they have to learn the programming behind it first, and it's a really easy way to do that. And then there have been studies that show pretty high retention rates for programmers who used Alice in their introductory computer science classes. So these studies are sort of why companies like Sun Microsystems are trying to make it universal so that people in other places can have the same options and opportunities that Alice provides. The latest version actually includes characters and scenes from The Sims, which was, and I guess probably still is, a really popular virtual reality world. So I guess they're trying to appeal to even more young people. And the most advanced students of Alice 3.0 get to the point where they just write standard Java programs rather than using the interface. And once they're done, they can export their work to YouTube, so add incentive. This example was like a dance party that someone made. It was kind of funny. And I just have a really quick example of what you can do with...
Do you need sound?
I don't think so.
Just say yes.
Okay. Yeah, it's not that interesting, but it shows, some movements some things you can accomplish with it.
How many of you guys have heard of the uncanny valley? Any of you? No? I'm in the uncanny valley right now. I'll show you uncanny valley in a minute. Questions for... Oh, did you want to do another one, too?
That's basically it. I mean, I can show the other ones, but...
Questions for Mr. Jeffers? Chris?
So what formats retention?
I guess for people who continue with computer science classes after their introductory course.
So if you take one more class?
I don't know. I didn't look that much into it. I would assume they mean farther into it, but...
How long do they use this Alice curriculum? Just for intro?
Yeah, so sometimes they just use it in like computer classes in like middle school, but then a lot of the times just for the intro class in like a college, so...
We're not going to go quite that cutesy in the end of this semester, but we are going to move into a language called processing after the next assignment, and I'm motivated by similar kinds of issues.
Yeah, this one's pretty simple actually. That's kind of funny.
I don't know if you guys notice that, but I definitely do. It creeps me out. So it's sort of like Shrek was a great movie, but the princess just is hard to look at in Shrek. It's just not quite human enough. And it's interesting. It's why if you look at cartoons like, the old Warner Brothers cartoons or whatever, you'll have an exaggerated feature, a big nose or weird eyes that are totally unrealistic. And we're much more comfortable looking at those than we are at looking at, what was it, Fiona, I think, in Shrek. Because they tried really hard to make her look actually human. And if you miss by a little, you miss by a mile. With this uncanny valley thing. It's weird. Like, this person is really creepy.
Yeah.
Right?
That person a robot?
Yeah.
Yeah.
The hands.
Yeah, so, anyway. Interesting psychological issue in computer science. Okay. Yeah, it's sort of like, the rubber mask thing, right? You see a lot of rubber masks in horror movies. And I think they're kind of leveraging that discomfort that we feel. It's not so much that the person's real face is concealed, it's that the mask is just really, even if it's like it's supposed to represent an actual person, the mask is just off enough to make us uncomfortable. All right, let's talk about using files in programs. Let's do this guy. So I've done a little prep here rather than starting from scratch. Let's look at this guy here. No, not that guy yet. I guess we could look at that guy. So to open a file, there's a new header that you have to include, and that's the fstream header. So this gives access to the ifstream and offstream file types, data types. Ifstream, an ifstream object is for input files, and an offstream object, not surprisingly, is for output files. And you can't do both at the same time. So you can't do both at the same time on the same file. Right? You can open a file to read it, you can open a file to write to it, but you can't open a file and then at one point in your program read from it and then at another point in your program write to it. And that's a fairly standard limitation in all programming languages. It's not unique to C++. And it really has more to do with the hardware that you're working on, because hard disk drives, which is where we store our files, are not really capable of reading from a file and then writing to that file at the same time. They either read from the file or they write to the file, but they have to be separated by certain things. Dylan?
So then, like, that whole idea of, like, enabling editing in, like, a Google Doc, it's kind of a cool breakthrough there?
Not so much. So then you begin to wonder, well, how is it that I'm able to edit my Word document, right? Because I open the document. When I open the document and load it into Word, I necessarily have read that file, right? And then I do clickety-click and I do save. And what have I done? I've written to the file. And so it gives the perception that I'm reading and writing to the same file. But actually there's what's called a buffer going on. So you read the file into this buffer, and then you close the file. And now you work on the buffer. And then when you're done with, you're ready to save, you click save, and then the buffer goes and gets overwritten on the original file. So we've all experienced the danger of this very paradigm, because you're working on the buffer and then the power goes out or the computer crashes. And what happens to the buffer? It's gone forever. And that's a standard paradigm in computing. You read the file into a buffer, you muck around with it, and then you save it. Sebastian?
So is the buffer stored in the RAM then?
It is in the RAM, but if it's extremely large, it can actually be stored on disk in a temporary file. So it may be that the file you're editing is so large that it won't fit into your RAM, in which case other measures are taken and it's stored in this unusual location on the computer. Ami?
Yeah, I think you just went into it, but I was going to say, is that like having a temp file that just sort of copies the file?
Yeah, and there are dozens of different ways of handling this very issue, but the takeaway for the day is that you have this separation between files that can be read and when they can be read, and files that are written and when they can be written. Okay, so let me comment some of this stuff out because it's not really relevant to what I'm currently doing. So I'm going to take this guy and shove it down below. Okay. Let me see if I have a file. I have lots of files. Like here's a file right here. So I'd like to read that file. So I'm going to tell my program what file it is that I'd like to read. I do this when I declare this variable input. So I'm declaring an if stream object, and it's called input, and I'm attaching it to an external file external called this thing input is called a file handle. We don't refer, we only refer to the external file name once in our program. That's when we declare the input file stream. And forever after, we access the file through the file handle, in this case, input. The beautiful thing is a file handle, an input file handle, act just like CN. So in lots of situations where you would use CN, you can use the input file handle. So let me show you that. Let's do something like I'm going to just declare a character, call it C, and I'm going to read a character from the file. And frankly, I don't even know what the first character in that thing is. So the first character in this file is a /. So when I run this program, if it compiles, let's see if it compiles. It does. Good. When I run this program, what will happen is the file handle will be attached to this external file. Then I will read from the file. And I'll read one character, and then I'll print it out to the screen, and then I'll close the file, and the program's over. if all goes well, I should see a forward slash. And I do. All right. The C. The C is up here, and it's a place to hold. It's a variable that it's a place to put that first character from the file. And I can do this as many times as I like. Let's do a little for loop here for int I equals 0, I less than, say, 10, I plus plus, and we'll get 10 characters from the file. And this is going to be rough, but let's just do that and that. So now what I'm going to do is I'm going to read several characters from the file. Let's see what happens. So the first thing that I got was the forward slash. The second one was the forward slash, then DESCRIPT. Let's go and look at that. That makes sense, right? Let's go a little bit further. I want to investigate some behavior. How far did I get? Let's just go out like 30. Okay. So you see DESCRIPTION:RANDOM, etc. Compare that to this, and what do you notice? No spaces. So there was a space between the colon and the R. And yet, if I get to here, it goes :R. This is something that we haven't really dwelled too much on up to this point, but reading characters using this syntax that we're using, this will ignore this is called formatted reading. This ignores invisible characters. And you might wonder, well, why on earth would I choose to do something like that? Why would I ignore invisible characters and just skip to the next visible character? It turns out to be really, really handy. I probably won't get to it today, but I'll get to it on Wednesday, talking about the differences. But suppose when I'm reading this file, I don't want to ignore the invisible characters. Is there a way that I can do that? And the answer is yes. I can tweak this syntax a little bit. I'm going to comment this out, and I'm going to replace it with the following. This somewhat unusual syntax forces us to deal with every character that we encounter, not just the visible characters. As I mentioned, these subtleties are things that we're going to be exploring in the next couple of days, but let me run this guy. And now we see that the space character is there. What happened down here, do you think? It actually found the line break character, the end line character, and it actually printed that to the screen. And when it printed it to the screen, it introduced this empty line. And then it went and found the first character in the next line. So let's go back and look at that. So it found the end line floating around out here somewhere, printed it to the screen, and then it actually kept going because I didn't really know how far to go, and grabbed the next character on the second line, the first character on the second line, and printed that out. So if you have a way of going through a file character by character, without ignoring any characters, you suddenly have a way of copying, in a sense. If I start doing this now, let's do cout C, and let's compile this guy and run it. I'm starting to see the beginning of that file. It's just going through character by character, and if I stretch this out, maybe go out to 300 characters, and I run it, I get the first 300 characters of the input file. What if I want to make a copy of this file? I can do that too. So this is all reading. If I want to make a copy of this file, what I want to do is open a second file and take the characters out of the first one and put them into the second one. Let's do that. So to write to a file, you have to get an output file handle. And the way to do that is use the offstream class. And let's give it a name. Let's call it copy, like that. I can go through the file, getting characters, and this is, let's call this an output file stream. And output is an output file handle. And it can be used like cout. Okay? So if I can go through the first 300 characters of this file, grabbing one character at a time, and then instead of printing them to the screen, I'll print them to the output file. And I will close the output file. So notice I have two files open, one for reading and one for writing. That's perfectly fine. What I cannot do is open the same file for reading and writing simultaneously. So I can't have this file here be an input and an output at the same time. I'll get a compiler error. Let's run this guy. Now the output won't be very interesting. In fact, we won't see anything at all. The evidence of what we've done is here. So remember, we were using this guy as the input file, and I called this guy the output file. The first 300 characters of this guy are now sitting in this guy, and let's open that up and see that.
So if we mess up and don't rename our output file,
Say again?
so like if we don't have a different name on our output file, then
Well, you'll get a compiler error. So let me try that, because I haven't actually done that. But so let's get rid of the copy here. So now we're trying to open for reading and for writing. And probably what I'm going to do is get a segmentation fault. No, didn't get that. I probably just wrecked my file or something. It's still there. I'm not sure. I just know that you can't do it, but I'm not sure where you're going to run into the errors when you try it. Okay, so I'll look into that. Okay. Now, if I really wanted to copy this thing, I'd have to go further, right? There were more characters in this file. So that raises the question of, is there a way to just go through the file and stop when I get to the end? The answer is yes. And so let me show you that. These little guys, these input and output file handles, have a lot more going on than just being able to read and write from the files. For example, if you try to open a file and the file's not there for some reason, you can actually check that and see that it failed to open the file. So here we can check for successful opening. And the way to do that is just if input fail, then we're just going to print out a message, failed to open file. And there are lots of more informative messages that you could print. And then we'll just quit the program. And I better put in that gives me the exit. So when might it fail to open the file? In what circumstances? Possibly. Or if I misspell it. So it tried to open the file named random array without the Y. It didn't find it there, and so it set fail to true. And so whenever you do something with a file, you should check to see whether it was successful or not. And if I run it with the Y in place, you'll see that I get past that if statement, no problem. Well, not only does opening, not only are we able to detect whether we successfully opened, we're actually able to detect whether we successfully read from the file. And typically what you do is right after you read from a file, you should check to see if you have successfully read from the file. And the way to do that is if input EOF, I'm going to break out of the loop. And then I'm just going to turn this into a while loop. And I'm just going to run it while it's true. So while this is true, which means it's just going to run forever, I'm going to read a character. I'm going to check to see if I'm EOF. And if I am, I'm going to break. Otherwise, I'm going to write it to the output file. What do you think's going on right here? What do you think EOF stands for?
End of file.
End of file. So I'll read from the file, and if I've tried to read past the end of the file, this is going to be set to true, and it's going to break the loop. And now I don't have to worry about how many characters are actually in the file. I can run this thing until it reads all the characters. So here's a very simple copy program. And the two files are here and here. Interesting that there's 300 there. I suspect that's left over from, I think I found my error, Sebastian. Open. Yeah, I suspect that when we tried that, it cut it off at 300 characters, and I didn't notice. So I'll fix that. We'll talk more about this on Wednesday. I see time is up.